Hello, physics fans! Today we're going to be looking at text problem 11-25 in your OpenStax, Volume 2. So, looking at this problem, we have a cosmic ray electron that enters the Earth's atmosphere perpendicular to the Earth's magnetic field. We're asked to solve for a radius of that electron's path. So, after reading this problem, we notice that there's going to be some magnetic force on the electron, so we need magnetism. Because we're working with forces, we need Newton's second law, and we're solving for a radius, so we need uniform circular motion. Our task, once again, is to solve for the radius of the electron's path. Our physics equations required are the equation for Newton's second law, the centripetal acceleration, which will be our acceleration in the radial direction, and the Lorentz force equation for a force due to a magnetic field on a moving charge. When we're drawing our problem, we have an electron moving with some velocity that is dictated perpendicular to the magnetic field. So I've drawn a perpendicular magnetic field coming into the screen towards me. We are given the velocity of our electron, the magnetic field, that these two are perpendicular to each other, so the sign will be 90 degrees. And then we are also given that it's an electron, so we know the mass of an electron on the back of your physics reference card, and the charge of an electron is the negative elementary charge. We're assuming that there are no other forces on this electron, and that it is a uniform magnetic field. So let's move over to the solve step. Because we're doing a Newton's second law problem, the first thing we have to do is draw a free body diagram. So we've isolated our electron. We've drawn and labeled the external forces on our electron, which in this case is only the magnetic force. We've drawn our coordinate axis, and because it's a uniform circular motion, we have the radial direction and a perpendicular y direction, and there are no critical angles which would be angles between our forces and our coordinate axis. So, starting with Newton's second law analysis, we sum all of the external forces and set it equal to the mass times the acceleration. In the y direction, there are no forces, and it is not accelerating, so we won't do the y direction in this part. However, in the radial direction, when we sum all the forces in the radial direction, it equals the mass times the centripetal acceleration. And the one force that we're working with in the radial direction is the Lorentz force. So the Lorentz force is equal to the mass times the speed squared divided by the radius of curvature. Now when we take the magnitude of our cross product in the Lorentz force, and we substitute in the charge and the mass of our electron, we can then write a total expression for Newton's second law in this case. And then we can simplify and solve for the radius of our electron in an algebraic expression. Once we substitute in all of our given variables, then we can evaluate the radius of our electron is 4.3 meters. Now checking, the units are meters because we're talking about distances. We have two significant figures, which is the least amount of significant figures given, and it seems like a reasonable answer. Thanks, physics fans. We'll see you next time.